Hello physics students, in this lesson we're going to take a closer look at conservation of energy with work being done. In other words, we're going to take friction into an account. We're going to take a look at something called the work energy theorem and and how that relates to the energy transfer in a system. So a little bit of review. We're going to take a look at energy being conserved, but we're going to take a look at it in terms of the system itself. Energy is always conserved. It's not created or destroyed, but it might transfer to other forms that are not included in the system, namely heat. And the way that it is mostly transferred is through friction. So when you look at a case without friction, like you're simply lifting up a child into a child seat, that's an example of potential energy, right? So the work done to lift that child, the force and the distance applied, is equal to the final potential energy. And so that's the case where there is no friction done, or no friction, so nothing's gained or lost. And energy can be conserved even if there is friction. It just will change into other forms that we're not measuring. So for example, it won't show up as a potential or kinetic. If this student is sliding across this icy patch and they slide at 5 meters per second and to a stop, if we know they have an initial kinetic energy and at the end we know that their final kinetic energy is 0, we want to know how much work is being done to cause that child to come to a stop. That's equal to the work that friction is doing. In other words, the friction is doing the work between the shoes and the ice, generating the kinetic energy, converting it into heat and thermal energy. And those amounts will be the same. So from that relationship, we get this idea of a conservation with work being done on the system. And so if something gains energy through a work situation, the force times the distance, then we know that it might have a increase in potential energy or kinetic energy or even spring energy. On the other hand, if it's going to lose energy by work done, like the sliding to the stop, the energy had to come from somewhere. Maybe it was a potential energy that was stored initially or a kinetic energy. These things get put together in kind of an energy chain, so we're going to look at a couple of those. And there's actually multiple ways of solving these problems. For example, we could use kinematics to solve something like this, where an engine applies 1,000 newtons of force over a certain distance. Starting from rest, the car has a mass of 2,000 kilograms. How fast are you moving after that distance? We could use our acceleration from the F equals ma, plug that into a kinematic equation, and find a velocity. We can also look at it from a work-energy relationship, where the work being done, the force times the distance, will equal the amount of energy that that car has after the interval. So it will equal the kinetic energy in this case, the 1/2 mv squared. We can then solve for velocity that way as well. You get the same answer. So the idea of using work energy theorem can be really powerful. So, for example, let's say we have a 75 kilogram skateboarder and they're kicking off. They have an initial velocity of 2 meters per second. They come to a stop after 15 meters. In your mind, I want you to imagine that skateboarder moving across the sidewalk, and they have, in this case, an initial velocity, and then they're coming to a stop. What's causing them to stop? It must be some work done by friction. So we can set the initial kinetic energy that they have, because they have initial speed, equal to the work done by friction, and work in this case is force times distance. So we can then set the initial speed of 2 meters per second in the mass and all that into the kinetic energy equation side equals force times 15. Why do I use 15 here? Because that's how far the work is being applied over. That's the distance that the work is being applied over. Alright, let's take a look at another one. We have a bullet that's moving along at 650 meters per second, hits a tree, and sticks into the tree to a depth of 0.04 meters. What is the force acting that the tree applies to the bullet to slow it down? Once again, we have an initial kinetic energy of the bullet, and then the tree is doing the work. It's applying a force over a certain distance. We know the distance from how far the bullet went into the tree, so that's a 0.04, and then we know the initial speed. We can then solve for force once we plug these numbers in. Once again, building this chain, this relationship, is the key physics idea. Plugging the numbers in, that's just algebra. But understanding that the initial kinetic energy is equal to the work done by the tree to stop the bullet is a key physics idea that we're going to continue to use in this unit. Please try these problems or similar ones on your quest. Let me know if you have any questions. Thanks.